rigorously. So I have a f of x, and let's, for example, x is in the interval 0 and 1. Okay. And my f h of x. So in this case, I'm actually approximating f with a function. I'm no longer only storing the value of the function f at particular points. I'm no longer only storing the average of f in intervals. I'm actually approximating f, a function, with another function. That's unique to finite element. Okay, I'm actually approximating the function with a function. But as opposed to this f of x, which can be any function, I'm constructing fh of x in a finite dimensional space. I'm allowing fh of x to be restricted. It cannot be any function. I'm going to give an example, the first example, right? F of x needs to be piecewise linear and continuous. If you remove the continuous requirement, it'll be our second case. Such that, so let's call all the functions that are piecewise linear and continuous to be the space of xh, right? Xh is all the functions that are piecewise linear. By piecewise linear, I wrote h being like piecewise linear in the intervals of size h. Okay, if I make h to be smaller, then the space is becoming bigger, because a piecewise linear function in the half h space is not guaranteed to be a piecewise linear function in h space, but a piecewise linear function in h space is guaranteed to be also a piecewise linear function in half of h space, right? Okay. So that fh minimizes the integral from 0 to 1 f of x minus let me just call it g of x square dx for all g of x within that xh. Okay. This is a projection. Why is it a projection? It's analogous to the projection in the physical space. So for example, if I have a pen over here, I'm looking at what is the projection of this pen on this table. The projection is going to be something over here, right? I mean, it's basically a projection, like a normal projection to the table would be like this. Or if I project the pen to the blackboard, it'll be like this. So why is it a projection onto the blackboard? Because first of all, like the x of h, I have a constraint. The projection has to live on the plane of the blackboard. Second, I'm looking at the closest approximation. I'm looking at the closest point or closest object on the blackboard to the actual pen. So that is why the projection of the pen is the thing here. Okay, so this is the projection in the physical space from a three-dimensional point to a two-dimensional point. And this is the projection in the space of functions. It is projecting a function f of x, which lives in the infinite dimensional space, to the x of h, which is a restricted space, is a subset of the space of all possible functions. Specifically, it is a subset with finite dimensions. And why do I mean finite dimensions? I'll explain later. Okay, it is a smaller space. But for it to be able to be represented by a computer, it has to be a finite dimension, of finite dimension. Okay. So this is projection. Okay. So let me illustrate why X of H is finite dimension. Has finite dimension. Because the space has what's called a basis. A basis that has finite number of elements, okay, or finite number of members, because it has a basis. Let me describe what this basis is. Well, let me first describe what a basis is. Okay, so a basis means if I have a set of functions, f1 of x, phi1 of x, phi2 of x, etc., phi n of x. So this collection of functions is called a basis. If for any g of x in the space, or in this context, for any g of x that is continuous and piecewise linear, we can express g of x as a linear combination. I go from 1 to n, a linear combination of these phis. Okay. Does it make sense? So that's what's called a basis. For example, our three-dimensional space has three bases. When n is equal to 3, it's going to be a basis. And phi1 would be a vector pointing that direction, phi2 would be a vector pointing that direction, phi3 would be a vector pointing that direction. Okay, for any point in the three-dimensional space, that point is going to be a linear combination of vector in this space, this space, this space, right? And a two-dimensional space would only have two bases, only one vector going there, one vector going there. Any point in the 2D space is going to be a linear combination of these two bases. And a function, if I don't have any constraints, would live in the infinite dimensional space, because you cannot find a finite dimensional basis that can represent, whose linear combination can represent any function, right? So that's why a space of functions can be an infinite dimensional space. But after this kind of restriction, if it has to be piecewise linear and continuous, it becomes a finite dimensional space. And let me tell you what this basis is. For example, I have a grid that is split into three intervals. In the finite element setting, it's called 3 elements. Okay, x, g of x. Let me try to construct these three bases. Not three bases. Let me try to construct a finite number of bases. So, the first basis is going to be like this. Let me here to be value of 1. The first basis is a function that goes from 1 to 0 and stays constant over here. Okay, let me draw the second basis using red. Starts from 0, goes to 1 over here, and goes back to 0 here. Okay, let me draw the third basis. The third basis is going to stay 0 here, and goes to 1 over here, comes back over here. So we have 3 elements, 3 bases. Do we have another one? No? Yes. What is the last basis? It stays 0 over here and goes to 1 over here, right? Okay, so why, so first of all these basis functions are within the space XH. Why? Because of course they are continuous and they are piecewise linear. Now the more interesting question is, why can we represent any function, any piecewise linear and continuous function, as a linear combination of these four basis functions? Think about it. For any g of x that is like that, right? Any function g of x. So this is actually phi of x. So for any function g of x, it is actually equal to, let me say this is 0, this is h, this is 2h, this is 3h. This is equal to g of 0 times phi1 of x. So phi1x, phi2, phi3, phi4 are these two functions, plus g at h times phi2 of h, phi2 of x, plus g of 2h times phi3 of x, plus g at 3h times phi4 of x. Right? Because this is the value of g at 0. g0 times phi1 of x would be equal to a function like that. Right? Okay. This would be the value of g0 times phi1 of x, which has the value of 1. If you scale it by g0, I would get a function like that. What is the second component? What is gh times phi2 of x? I would get a function that has the same shape as phi2 of x, but has a different height. Instead of a height of 1, I would get a height of gh. So this is gh. A height of gh would get me a function like that. Right? What is the third component? I'm going to get a function looks like that. And the fourth component, I'm going to get a function that looks like that. If you add all of them together, we are going to get the original function. We are going to get this function. Right? So this is a proof that for any function gx that is continuous and piecewise linear, it can be represented as a linear combination of these four basis functions. Or in other words, this particular function space that is piecewise linear over these three elements and continuous is dimension 4. Okay, we are looking at a 4-dimensional space. Any point in the 4-dimensional space is actually a function that looks like the black function over here. Does it make sense? And if instead of 3 intervals, I have 100 intervals, what is the dimension of the space? 101, because I'm going to have 101 basis functions. I have 101 grid points, right? And every grid point can have a basis function whose value is 1 at that grid point and 0 at all the other grid points. If you combine all of these basis functions, it's a complete basis of the space. Okay, so now we get a finite dimensional space. Any function g within that finite dimensional space can be represented by a finite number of floating points in my computer, right? Because I only need to store the value of the function g at these grid points. And that's sounds similar to finite difference, but actually the meaning of these numbers are completely different. In finite difference, we are just storing the value of the function at the grid points with no idea of what lies in between these grid points. And in finite element, after we store the function value at the grid points, we know exactly